Hello.
Hello.
Okay. So let's begin. Where did I leave off last class? This one?
Yeah.
Okay. Um, by the way, I think I mentioned a little bit about circular motion that day. I just want to extend it a bit. That is, yeah, because you have a bit more in your syllabus. So like I said, when an object is moving in a circle, its velocity is changing. Okay. Why? Because when it is moving, you can see that the direction is changing. Okay. Yeah. But the magnitude is the same. Like I said, why is it changing direction? Because it is like always facing a force that is directed towards the center of the circle. Okay, this is what we call centrifugal force. But in your case, I think you just need to know that there is a force that goes that is directed towards the center of the circle. So let's say if we look at the object right here, let's say that it is moving in this direction, which is this one. I'm just showing this part right here. So the force that is directed towards the center of the circle, that is actually acting perpendicular to the direction of the velocity. So this is the centrifugal force. And this is the object's velocity. Okay. So every time, like at any point, you will see that it's the same. There's a centrifugal force that acts perpendicular to the velocity. Okay. Is that clear?
Yeah.
Okay. Centrifugal. All right. I just thought that I missed it out, so I just clarified it. All right, so I think we're done with dynamics. Let me check, what do we have next? Mass, weight, and density. And then we have turning effective forces. Okay.
Apo, in our dynamic syllabus, number 8, it's the same thing as you just described, right? Discuss how ideas of circular motion are related to the motion of planets. In this,
Oh, okay.
I'll
No,
just say
I
the same
was-
thing as this motion.
Oh yeah, yeah. The thing is, I just explained to you, I think, G, yeah, describe qualitatively the motion in a circular path due to a constant perpendicular force, which is this one, the centrifugal force that I talked about. Now, it's the same thing for an electron in an atom, right? So, for example, let's say this is the nucleus, and the atom is like circulate. It's not the atom, sorry, the electron. Okay. The electron is moving around the nucleus, right? Why is it moving like that? Why is it moving at the same speed but different velocity? I mean, it's changing velocity because it's changing direction. Because there is a constant force that is acting towards the center of the circle, which is the nucleus. And now the force that the electron is feeling is actually the electrostatic force. This is what is, acting as the centrifugal force. In this case. So again, our velocity, let's say, is towards this side. The electrostatic force is always acting perpendicular to the direction of the velocity. And in the same case, if you think of, I don't know, maybe a satellite, then let's say this is Earth, and the satellite is moving around the Earth. So what centrifugal force is it facing? The gravitational force, right? So here the gravitational force is the force that is acting perpendicular. That is the centrifugal force. It's the same thing. I hope that's clear.
Yeah.
Yeah, the formula that F equals to mv squared divided by r, you're going to learn that in A levels. It's not necessary right now. Discuss how ideas of circular motion are related to the motion of planets in the solar system. Yeah, when you think of the solar system, I mean, the planets moving around the sun, this is also the same thing. It's just a greater gravitational force that is acting. Not, yeah, gravitational force still.
So with satellite, and if it was any other planet, it's still facing the gravitational force.
Exactly. It is always like like in A levels, I think you would study that, any two planets or even any two, I wouldn't say objects, any two matter, okay, they actually have this sort of attractive force towards each other, and that is what we call the gravitational force. So this acts between every planet or every matter or every star. So whatever is around, circulating around something, it is facing that attractive force. It is the same thing about the moon and the earth. Yeah, the moon circulating around the earth, it's the same thing. All right. Is that clear?
Yeah.
Yeah. So that's what gravitational force is all about. When just two matter they attract each other. There is a force between two matter, that is gravitational force.
Yeah.
All right, I think we're done with dynamics. All right, let's start this mass and weight and gravitational fields. Okay. What is mass?
It's an amount of like a substance.
Yeah, it's a measure of the amount of substance in a body. Yeah, we already know the SI unit. It is kilogram. Now, next point is that mass actually depends on the size of the body. And the number of atoms it is made of. All right, so another thing is that it is a scalar quantity. Okay. Do you have inertia in your syllabus? I guess so.
Yeah, but I think we do.
Okay, so inertia is the measure of resistance, is the resistance of a body to a change in motion. Not just motion, I guess, resistance of the body to change in its state of rest or motion. Okay, now obviously, the higher the mass, the higher the inertia. The more what else? Now to overcome inertia of a body, obviously a force has to be applied. And this force is dependent on the mass as well. Obviously, because mass also depends on inertia. Next, gravitational field strength. Um, what is it? It's the gravitational force acting on a body per unit mass. All right. On Earth, for now we will take it as a constant. So 10 Newton per kilogram. And on the moon, it is much less, which is 1.6 Newton per kilogram. Okay. Now these are very approximate values, of course, but it's okay to learn 10. Usually it's 9.81 or even 9.889, whatever. Now, the question is, if we define gravitational field strength as 10 Newton per kilogram, why do we actually sometimes write it as 10 meter per second square? Or what is it actually? 10 meter per second square.
The acceleration.
Exactly, that's the gravitational acceleration. But they have the same value. Why? Because just think of an object which weighs 1 kilogram, and let's say it's falling downwards with a weight of 10 Newton. Okay. So if you use the Newton's second law, which was as opposed to ma, you see that the acceleration is actually 10 meter per second square downwards. Okay.
Apple, we got 10 meter per second here only because of the mass or the weight of the object, right? Because it's 1 kg. But if it was something else, then it wouldn't have been equal, right?
Exactly. That's the thing. The acceleration as an object falls, it actually depends on the mass. So if it was, let's say, like 20 kilogram object, then obviously its weight is higher, which is, let's say, 200 Newton. So if you want to find its acceleration going downwards, then it's 200 Newton equals to 20 times 8. Oh, it's the same. It will always be the same, actually, yeah.
I'm done noting.
All right. Now weight. What is it? The gravitational force acting on an object of mass and motional force let's see, acting on an object of mass m. So when a body falls, its gravitational force or weight can produce an acceleration, which is g. Okay. Using blah, 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 using Newton's second law, we have W equals to mg. So are there any questions?
No.
Okay. Now the differences between mass and weight, if they ever ask you. Mass is the amount of substance in a body, and weight is the gravitational pull of the body. Does not depend on location. Does depend on location. More like it depends on the gravitational acceleration. So yeah, which changes due to the location. That's why. Measured by beam balance and measured by a spring balance. Unit is, for example, kilogram, and this one is Newton. Okay, that's that.
Apu, for the measurement, we just need to know that they're measured by either a beam balance or a spring balance. We don't need to know how to do it or the procedures of that, right?
Actually, I think you do. You need to know, how to use a beam balance, and at least not how to use. You need to recognize a beam balance and a spring balance. That's a very good question. I'm actually going to show you just after we're done with density. Okay.
Yeah.
Give me a minute. I'm coming back. Okay. Let's start with density. Yeah, if an object is denser than the liquid, the object will sink. That's it with mass, weight, and density. I think now we can move on to turning effect of forces, but before
This
that,
is probably. I'm sorry, this is probably a foolish question, but what if like the density of the liquid and the object is equal?
yeah, then yeah, good question, actually. I mean, even for, I don't know, maybe 0.001%, there might be a difference. So the lighter one will be on top. Now, it really also
Yeah.
depends whether the two things, do they dissolve in each other or not? So if they dissolve, then obviously they will be dissolved. I mean, otherwise
Yeah.
it will always float or sink.
Yeah. Got it.
All right. Yeah, beam balance, right? So a typical beam balance is the one, I think almost everyone has seen it before in their lives. Um, so usually you have this two plates. Yeah, that's how we measure mass. Why? Because we always need a reference. So you have to put a reference that is, let's say, exactly 1 kilogram. You define it as 1 kilogram, and then you put the object that you want to measure, the unknown, the want to measure the mass of, and then obviously depending on how low it gets or how up it gets, you actually make a sort of measurement, you know, an approximation, like uh, about its weight. That is the basic of beam balance. It's just a sort of comparison. Okay.
Yeah.
Obviously in the lab or anywhere, you don't get, you know, these are old designs. Obviously you don't really need to put something like, you know, 1 kilogram and then put your object. You obviously have a scale that is built in, so you just have one plate, and let's say you have your, I don't know, scale or something like that. You just put your object right there, and then you typically see your value. What about a spring balance? Yeah, a spring balance usually is like, you know, a hook that has a scale, and it measures the force with which something, I don't know, pulls the spring downwards. Okay, so it sort of measures the force with which it goes downwards, and then the scale will tell you the weight. This is the balance. All right, I think in your book there are better explanations and maybe also some exercises. You can look through that. Okay. All right. Okay. Next chapter is turning effect of forces. Let me check your syllabus first. Okay, can you check and ask me if you have any question from the previous chapter, mass, weight, and density? Did I miss out on anything?
This one thing. Describe how to use a measuring cylinder to measure the volume of a liquid or solid. I know the liquid, but for solid, I think I'm a little bit confused. Using a measuring cylinder.
Okay, so do you want me to describe that? Hello?
If possible, yes.
Yeah, sure. Okay, so obviously we know that measuring cylinder is just like a cylinder, and it is used to measure volume. So it has, like, you know, scales in it. So simply, when we want to measure the volume of a liquid, it's simple. We just pour the liquid in and we will see, you know, exactly where it corresponds to. That is the case for a liquid. That's easy.
Yeah.
But what if we want to find the volume of a solid, a small solid that fits in a measuring cylinder? So we first pour a bit of liquid. So let's say we have this liquid that is like right here, and then we obviously note it down, and then we put our object, whatever it is, let's say a stone, and then we will measure the rise in the volume. So let's say the liquid, after the object is put inside the measuring cylinder, let's say the volume increased up to here. Okay. So then you just simply deduct the initial value from the final value to get the volume of that object.
Yeah.
So let's say this is the final F and this is the initial. So the volume of the object is just F minus I. Yeah, maybe it's centimeter cube. Okay.
Yeah.
That's it. Anything else?
No, I think the rest is covered.
Okay, great. Moment, center of mass, stability. It's not the moment of force in terms of its turning effect in the latest. Okay, let's first talk about moment. What is the moment of a force? Moment is basically the turning effect of a force about a pivoting point, which is a pivoting point. Yeah, a point that is, like which stays stationary and the rest of the body tends to move. Okay, so that's the pivoting point. You'll know in just a moment. Okay, so what is the equation of moment of a force? For force time the perpendicular distance. So F is the force, D is a perpendicular distance of line of action of F from pivot. Okay, so for example, let's say this is our pivoting point, and let's say this is a wooden bar, and a force is being acted at this point. So this is F. So you'll typically draw a long line like this. This is the line of action of force F. Okay. And then the distance from the pivoting point to the force is called D. So if you multiply F with D, you get the moment.